All right, so the first speaker of the second part session will be Lam Hui, who is going to talk about magnification and degradation.
When Brice and Olivier asked me what I want to talk about, I couldn't quite decide, so I gave them actually two topics. And I still couldn't decide, so I think I'll talk about both. One of them is obvious, the other is not so obvious, and you can decide which is which. But at the request of Lev, I'm going to switch the order of the obvious and the not obvious. So here's what I'm going to do. I'm going to skip ahead.
Why don't you start backwards?
Sorry?
Let's do it backwards. That will be...
Backward. That would be confusing. Or beyond comprehensible, as in Gary's title. So I'm going to talk about degravitation first. This work done with my colleagues at Columbia. And so here's the idea. So let's consider an action. I'll do this in 4D, although you can actually extend it to any number of dimensions. We want to build an action which depends on a metric. Of course, we have gravity. And I represent some extra degree of freedom. It could be some scalar field, but it doesn't actually even have to be a scalar field. I will just call it phi. And here is the famous cosmological constant term, yeah? And m here is the Planck scale. The cosmological constant is naturally something very large, Planck scale. And I put an alpha here. It's just a dimensionless coefficient. It's of the order Planck scale, but you know it could vary up and down. Alpha is order 1, let's say. Back in '89, Steven Weinberg, if you look at his famous article on the cosmological constant problem, he proved a number of no-go theorems on basically attempts of this sort to build a Lagrangian or an action such that the following is true: that the metric is Minkowski for arbitrary alpha. For arbitrary, you know, if you dial your cosmological constant, which is presumably sensitive to UV physics, physics at high energies, somehow you want to build an action that is insensitive to that you can always find solutions where, in some sense, the vacuum energy doesn't gravitate, essentially. Yeah. So that was actually Weinberg's attempt, and he has proved this theorem, which has kind of a mythological status that basically says no, it's impossible, you cannot do it. A modern version of this kind of attempt would be to actually slightly modify what he did, was to say, well, let me find an action so that maybe I don't actually quite need the solution to be Minkowski. I want actually a cosmological solution where the curvature or the Hubble constant is much less than the Planck scale for arbitrary alpha. And of course, at the same time, we know we love inflation, so you want to allow inflation also. It might seem this is something very hard to do. And so let me first off say just a very simple example, right? So let me build a Lagrangian where I explicitly add into the Lagrangian a cosmological constant term that basically more or less exactly cancel this term. Clearly, such a Lagrangian would actually give you low curvature solutions or even Minkowski solutions if you fine tune. However, the point being, once you actually dial this number alpha, then your fine tuning is broken. Essentially, basically, you want to find a Lagrangian or an action such that you have this low curvature solutions that is stable against, you know, basically your UV physics, your high energy physics, or quantum corrections to the cosmological constant. So that's what you want to do. And I will have something to say more about Weinberg's no-go theorem in a second. So how do we make progress? You know, this is some arbitrary function of the metric. So the way we'll try to make progress is to let's just focus on basically homogeneous isotropic universe, i.e. the Freeman-Robertson-Walker metric. The fact that you can write the metric in that form doesn't actually depend on your theory of gravity. It only depends on symmetries. And if you restrict to homogeneous isotropic universe, then the metric actually have only one free function, which is the scale factor. And so you can actually rephrase the problem this way, where the Lagrangian, I have factored out basically a cubed. That's an x here that's missing, d4x. A cubed, which is basically just the square, the determinant, the square root of the determinant of the metric. I factor out the Planck scale here, m squared, and then I replace the Lagrangian, which is now a function of only basically a dot over a, the Hubble expansion, and some extra degree of freedom, which I call phi here. And then this is the cosmology constant term, when you restrict to FRW universe. Again, I have d4x missing here. This is actually very general. Even if your Lagrangian have actually higher derivatives in A, let's say A double dot, A triple dot, you can always integrate by parts. And in general, you can always write as just a function of H. If you restrict yourself to isotropic homogeneous universe. And then the equation of motion is actually fairly simple. We are going to follow Weinberg and assume that we want to seek solutions that are static in phi, so constant phi. The equation of motions is basically dl d phi equals 0. That's one equation. And then the other equation of motion basically comes from time reparameterization invariance. This is basically the equation that tells you, in some sense, the Hamiltonian is 0 of the system. And that follows from time reparameterization invariance, or if you want, you can actually just take this and vary h. And then integrate once, then you get this equation. So these are the two equations. And if you look at this, stare at it for a while, you can actually write down a general solution. You can actually ask, I want to just come up with some function L of h and phi such that I always have solutions where the curvature is very small in spite of having a very large cosmology constant, which means a very large Planck scale. And basically satisfy both equations. And this is something that actually it turns out you have almost infinite freedom to choose what this function is. And what I want to do is to show you one particular example that we come up with, tell you the progress that has been made, and the problems. There are, of course, problems. But before I do that, let me tell you one thing about Weinberg's theorem. So Weinberg's theorem actually follows from, in some sense, a very restricted assumption, which is the following. He actually wants to seek solutions that are static, i.e. static in phi, and actually the Hubble expansion is 0, so it's just Minkowski. If you want such solutions, if you look at these two equations, clearly you have basically two equations for the same phi, which in general is overdetermined. And so in Weinberg's case, he has to actually impose a condition that relate these two equations, that they are redundant, they are not independent. And from that, he managed to show that the only way, the only adjustment mechanism is via conformal symmetry. But once actually you depart from demanding that h be 0, in fact, these two equations are two separate equations for two unknowns, h and phi. And they no longer have to be actually redundant. And so the situation actually could be quite different. So this is all very abstract, so I'll show you one example.
You assume GR or not?
I'm not assuming GR, right? This L is actually very general. In fact, in the next slide, I'll show you something that's actually not GR. So this is what you might want. So if I go back to this equation, let's say I solve the first equation for phi as a function of h. I can substitute into the second equation and just completely eliminate phi. And so you have a single equation for h. And let me show you an example. And the example I show, we call it seesaw, and in the following sense, yeah? Let's ignore this second term for now. This term is precisely basically the GR term, yeah? The h squared would be proportional to m squared. If that's all you have, then you have the Cosmology constant problem, right? that m is very large time scale, but the observed Hubble constant is very small. So that's the regular GR term. But let's say you, instead of having that solution alone, you have an extra actually term which gives rise to actually multiple solutions, which goes like this. Little m here is just another mass scale, some mass scale, to give you the right dimensions. But the point is this term actually allows solutions where the cosmological constant is very large, but the curvature is very small. And that's the kind of behavior you want. You want to have, in fact, in view of the fact that you want inflation in the universe, you actually do want behavior of this kind, which we call seesaw. You want your gravity theory for a large cosmological constant to give you multiple solutions, some of which has high curvature, which allows inflation, some of which have low curvature, which allows, explanation for what's going on today. And ideally, you would like to have the right dynamics to make the transition from high curvature to low curvature. So that's the idea. The question is, how do you realize this kind of seesaw behavior in a sensible theory? And the step from this to writing down a Lagrangian is actually very non-trivial. There are actually many degrees of many ways of doing it, and they are all inequivalent. So to go from here to here, what you want is to somehow put back your scalar degree of freedom, and you want to actually write your action in a form that is actually covariant, meaning not just in terms of H, but in terms of the actual, GR covariance. And so this is an action that we came up with. So this is the usual Einstein-Hilbert term. This is just some scalar field with some kinetic term. And the scalar field has coupled to G is basically what is called the Gauss-Bonnet invariant. It goes like R square. And the nice thing about the Gauss-Bonnet invariant is it is a total derivative. It's a topological term. So it has coupling between phi and this R square. And then we add a linear term, J phi, and then here is the cosmological constant. So why go through all this, why have all these complicated terms? You can actually check for yourself. If I actually seek basically solutions where phi is static, just like Weinberg does, basically you ignore this term. If you actually vary the action with respect to phi, you can see phi basically should goes like J over basically the Gauss-Bonnet invariant. And remember, the Gauss-Bonnet invariant is R squared, which is essentially h to the fourth power. So what we have here, the Einstein-Hilbert curvature is roughly h squared for Freeman-Robertson-Walker universe. So the Gauss-Bonnet is R squared, so that goes like h to the fourth. And so you can check for yourself if you integrate out phi and put back in how phi depends on h, you will get actually a 1 over h to the fourth term in the action. And so to put it more precisely, if you vary the action with respect to phi, you would see a term like phi times g, which is h squared, h to the fourth, goes like j. And so if you substitute phi equals to j over h to the fourth into here, you will recover in the action precisely terms like h squared and 1 over h to the fourth. Precisely the seesaw behavior you want. And this is not a crazy looking theory, actually. From string theory, for example, you expect these higher curvature invariants, and they should be coupled to the dilaton. And so this is not completely crazy. So what have you achieved? So this is the kind of progress and the problems. Let me just summarize. If you work out the detail of this model, here, let me talk about the progress. Number one, it turns out you can show in models of this kind that this model have the nice thing is stable against quantum corrections, i.e. the low curvature solution, which is basically a low curvature balancing a high cosmological constant, that is the low curvature solution. that it turns out that solution is stable against basically your UV physics. If you renormalize your cosmological constant, even if you renormalize actually parameters in your theory, the mass of the scalar field, for example, is actually stable. So that's nice. That's what our particle physics colleagues call technical naturalness. And the other interesting feature of these theories is that it turns out it makes connections between large-scale and small-scale GR experiments. By large scale, I mean basically cosmological scale experiments, such as the ones that have been discussed, such as what Roman has discussed. And small scale, I mean solar system tests. It turns out, at least in some of these theories, there's one prediction, which is the following. That if the parameters of the theory are chosen such that the effective equation of state differs from -1 by an amount that's observable, then you should also see deviations from GR in solar system tests just around the corner. They are actually more or less, by some coincidence, in the same ballpark in terms of the parameter space. So that's kind of nice. At least for some of these theories, you have a more rich phenomenology. You can actually test these theories using solar system tests, such as lunar ranging experiments and the large-scale cosmological tests. And the same actually is true actually in DGP, for example. You can make the same statement about DGP. Problems. We do have fine-tuning. I mean, if you think about it, we have a small parameter in the problem, clearly, which is h over m Planck. The observed Hubble constant divided by m Planck. It's very, very small. And no matter what you do here, seesaw or what, you are going to have a small parameter in the problem. And so that's fine-tuning. I call it it's the issue of psychological naturalist versus technical naturalist. Of course, the ultimate goal is actually to explain where the small parameters come from, and we don't have an explanation for it. So that's one problem we have. And the second problem is probably even more severe, is dynamics. I mean, so far, following basically Weinberg's approach, we have been looking for static solutions. But you want to ask ultimately, how does phi get to where it is today in order to have the low curvature solutions? And we don't have an answer for that either. Basically, what one really wants is to have a high curvature solution that is unstable during inflation, so eventually you roll away from high curvature, and then a low curvature solution that's stable, so that eventually you'll get there. In our model, it turns out it's the reverse. The low curvature solutions is unstable. So we don't have a good actually answer for how do we actually get to where we are today. So that's another problem. So, and I view this problem as pretty severe, really. We haven't really solved the cosmological constant problem. We have made some progress in these two fronts, but we haven't solved the problem, certainly. A few comments. Ignore this residual test. I don't know why that's there. Forgot to delete it. A few comments. It turns out this framework is actually very general. In case you think the best we could come up with is basically scalar tensor theory of some sort. This is basically essentially some kind of scalar tensor theory. Although here, usual scalar tensor theory have the scalar coupled to the Einstein-Hilbert action. Here it's coupled to the Gauss-Moneta, but it's still some kind of scalar tensor theory. But it turns out this framework is actually more general than that. This framework is actually general enough to encompass DGP that Roman talks about, or more generally even massive gravity. And it actually makes connection to this whole idea, which was actually called degravitation by Justin Curry and collaborators. It turns out this framework you can actually discuss these ideas. And secondly, is a point I want to emphasize. I mean, nearly all current dark energy or modified gravity model ignores the cosmological constant problem, right? So in DGP or in quintessence, it's postulated that some mysterious mechanism just set it to zero, the fundamental cosmological constant to zero. And the original cosmological constant problem is actually there. And it seems one might make some progress by actually asking the questions. Well, let me build models that give us acceleration today, just like quintessence or DGP, while also actually hoping to solve the cosmological constant at the same time. Maybe that give you more constraints on the kind of models you can build. Because after all, for quintessence, you can just write down any potential you want to do what you want. But actually demanding that somehow you solve the Cosmology constant problem might be the additional thing you want to do to impose on the class of theories you want to write down. And it might be so constraining that maybe it's impossible. We don't know. We certainly haven't solved the problem completely. But it seems worth thinking about. Let me turn to some generic kind of structure formation or cosmology predictions of these kind of theories. And this is actually very much related to what Roman talks about. So here are a few. I don't think I'm listing all of them, but a few generic predictions where you modify gravity, or if you like, if dark energy have a complicated clustering behavior. For example, from the four-dimensional perspective, you should have, in general, two scalar metric perturbations, and in general, the phi and psi are different, as Roman talked about. Number two, the relation between the growth observables and the geometry observables, geometry meaning just measuring distances, growth is the growth of the first-order perturbations. The relation between them is different from GR. There have been a lot of papers on exploring this kind of test of GR. And then lastly, also actually shown in the DGP example by Roman, that in general, you expect the growth factor to be scale dependent. And these are things that one can go out and test, for example, with quick lensing data. And I'm going to focus on basically these two. I'm going to focus on the second and the third, give you some examples. So how do you test whether the relation between the growth of observables and the geometrical observables is consistent with GR or not? In principle, the best thing to do is if you actually know a theory or a model, you should just test that model, test the predictions of that model. But in the absence of that, here's one simple thing you can do. It's a very terribly simple-minded consistency test. We call it parameter splitting, which is the following. When you fit data with a whole bunch of parameters, usually you have a dark energy parameter like W, the equation of state. You can always split it into a what we call a geometrical W and a growth W, i.e. the geometrical W controls only distances, whereas the growth W control only the growth of perturbations. And you can always fit your data without demanding these two are equal. In GR, they would be equal, but you don't have to demand they be equal. Just fit two parameters instead of one. And that would be your consistency test. You want to ask if data is consistent with the two being equal. And this is something actually Wiley Wang, he's now a postdoc at Chicago, who was a student at Columbia, has done to a variety of data, basically all the data up to WMAP3. And this is the kind of split. This is the geometrical W, this is the growth W. This is, if you like, this is the GR line where they are equal. There are all kinds of data being used here. I won't go into a lot of details. There's microwave background, there's supernovae, there's galaxy power spectrum, there's even weak lensing. If you combine all the data, you get basically the solid contour. It's consistent with the two being equal. So if you like this, you can think of this as a confirmation of GR, although the error bar is fairly large. One caveat I should say, though, this is precisely using the kind of thing that Roman said we shouldn't do, using basically linear Poisson's equations. So to the extent that at least some of this data, for example, particularly CMB, is sensitive to basically scale way above the nonlinear scale, this is probably okay. But to the extent some of the data, for example, the weak lensing data, actually go down to basically nonlinear scale, this is probably not okay. So one has to be a little bit careful about it. But with that caveat in mind, this is actually a point that approximates the DGP fairly well if you use the linear approximation. If you use the linear approximation, the growth of structure and the distance scales is actually approximated by more or less actually this point. And so the DGP, if you, with all those caveats in mind, appears to be actually inconsistent with data at about 3 sigma level. Most of the constraining power is actually just coming from supernova. The fact that W, is different from -1 in the DGT model. Some of it is actually coming from large-scale structure. In particular, from the fact that DGP would predict the CMB quadruple would be actually much higher than what is observed because of ISW. And right now we are doing a more careful calculation of this without actually basically just splitting parameters this way of DGP. But it looks like certainly I think it's fair to say there's tension of DGP with the data. And then I want to say something about this issue of scale-dependent growth, that I talk about here. Ideally, for example, eventually from weak lensing, we would have measurements of, let's say, the mass power spectrum as a function of redshift. And if you go to the linear scale, then GR should tell you the ratio of this power spectrum should be scale independent. This is something you can test, and hopefully we can test. What I want to emphasize a little bit, something slightly different, is that you can do this test even from measurement at one single redshift, even without comparing mass power spectrum with different redshifts. And here's how you might do it at just one redshift. And it uses an idea that goes back to Jim Fry. It's a very simple idea. It's a very elegant idea, which has to do with how we think galaxy bias evolves with time. So these black dots here represent dark matter particles. Red dots represent galaxies. Galaxies form at some point in our past with some bias, let's say. They don't trace mass. And the point is this. As long as both the dark matter particles and the galaxy particles move on geodesics, which in most of these modified gravity theories is true, including GR as a special case, then as long as they respond to the same metric perturbations, respond to the same gravitational potential, eventually the dynamics should drive them to trace each other. Yes, regardless of your theory of gravity. As long as they respond to the same metric, that's what they should do.
If there is no merging.
If there's no merging. So Jim Fry's argument has no merging. So this is an important caveat to keep in mind. But the point is, you can work out basically the evolution of this bias, and you can basically show the bias should evolve like, should asymptote to 1 if you have a lot of growth in the future, plus some constant times the growth factor. And the point is this, if you modify gravity in general, your growth factor is going to be scale dependent, which means your bias, even if the initial bias at formation is scale independent, is going to develop a scale dependence just because of this evolution. Yes. And so here's a pictorial way of showing it. So let's say I'm plotting the mass power spectrum here as a function of K at 2 different redshifts, redshift 3, redshift 0. And I'm exaggerating here, of course, but here is meant to show that you have some modified gravity theory where on large scales the growth is suppressed, so the power spectrum changes shape. Yeah? And let's say your galaxies form at redshift 3 with a galaxy power spectrum that has the same shape of the mass power spectrum, i.e. the initial bias was scale independent. And the galaxies would want to evolve to a galaxy power spectrum that actually follow the dark matter power spectrum at redshift 0. But it turns out that relaxation process takes time. And so in general, at redshift 0, your galaxy power spectrum is going to have a shape that is different from the initial one and the final one. It will be somewhere in between. In other words, your galaxies are going to have a scale-dependent bias in general. And of course, this argument, which is basically this equation, ignores merging, as Roman correctly pointed out. We are doing a calculation which actually includes merging. Basically, do the usual random walk calculation with the scale-dependent growth factor. I mean, we expect the scale-dependent is going to survive. There's no reason for it to just completely magically cancel out. It should be there at some level. The question is how much. So, in general, you should expect a scale-dependent galaxy bias. And so here, just a hypothetical example. Here is basically, we show a hypothetical example of one where you just, again, modify the Poisson's equation in a linear way by adding a Yukawa term, giving it a mass. And let me show you galaxy type A and type B and show you the bias. Let's say galaxy type A form at redshift 5 with a scale independent bias. As it evolves forward, the bias tends to decrease. It wants to reach 1, but actually it doesn't quite get to 1 because the growth is actually slowed down by acceleration. But the point is that at large scales, at low K, the evolution of bias is really slow by a lot if you modify gravity, for example, this Yukawa modification. And so the bias becomes scale dependent. Likewise for galaxy B, which is just kind of an opposite example, it has a bias less than unity, and it forms a redshift 2, and then evolves to have a scale, also a scale dependent bias. Basically, the point is the bias evolution is slowed down at low K, at large scales, which is probably true for a lot of these modified gravity models that are constructed to explain acceleration, because gravity is weaker on large scales. And so if you take the ratio of these two quantities, which is what you can directly measure, you can measure the galaxy power spectrum of galaxy type A and type B. Let's say they form at different redshifts. You take the ratio, you should check, and you can check whether the ratio on large scales, of course not on nonlinear scales, on large scale, whether it's consistent with a scale dependent or independent bias. So it's kind of a null test you can do. And by the way, there have been a lot of interest on how primordial non-Gaussianity introduces scale dependent bias. This can do the same thing actually. Of course, it depends on your model. How much, to what degree you have this scale dependence. So I think I'm probably out of time. So
maybe we can stop here.
Yes.
So we try to have another talk this afternoon.
Of course. Okay. Sure.
So let's start. Any questions for Lam? Chris?
Just a comment on this
Yeah.
business of the linear regime. So in some of the modified gravities, such as the amplifier gravities that have a scalar that turns off inside of halos.
Yes.
These theories do not put bases of position, so it's not
Right.
clear to me that they even have a linear regime, because the matter of the false halos ceases to be a source for the scalar field.
Right. Right.
And the other thing this would do, which would lead, I think, to an additional contribution to our scale-dependent bias,
Yes.
would be that the large-scale gradient in the scalar field will not fall on objects in the halos. You would not necessarily expect the galaxies and dark matter to fall at the same rate.
You mean the galaxies and the dark matter, they do move on geodesics? So it's a frame-dependent statement. If you go to the Jordan frame where both are minimally coupled to gravity, they should just both move on geodesics. If you believe that's the physical frame.
Locally, that's true. Like the galaxies sit in halos.
Yes.
A lot of the dark matter either sits in lower mass halos or not in halos at all. So you might expect that averaged over some bulk sense, averaged over scales of 10 megaparsecs, the peculiar velocities of the galaxies and the dark matter need not be the same.
So you're saying somehow nonlinear interactions causes the galaxies not to move on geodesics. Is that what you're saying?
I'm saying
Yes.
that a galaxy is not a point object.
It's not a test particle like the dark matter particle.
It's not a bulk object that screens out the scalar field.
Yes.
So I don't see why the bulk acceleration of the halo should be the same as the bulk acceleration of a lot of dark matter particles.
Yes. Yes. I mean, there certainly could be funny nonlinear interactions going on. I mean, in some sense, that's the point of Roman's talk. Yeah, that in some way, we know of two different suppression mechanisms on small scales. One is in DGP, basically you have this basically cubic interaction term in the Lagrangian, so you have strong coupling on small scale which suppress the scalar field so that you are consistent with GR on small scales. The other mechanism is kind of like this F of R that you were referring to, where you basically use something like a chameleon mechanism so that the scalar field becomes massive on small scales, which also suppresses, makes it short range, and so you can satisfy all the known GR tests. I mean, it's possible there could be funding on interactions that make the galaxy not move on geodesics. I'm not sure I understand exactly how that might work. But it's certainly an interesting thing to look at. Yes, so what I said here is certainly assumes the galaxies and the dark matter particles move on geodesics. And at least to the extent you can think of them as test particles, and the Jordan frame is the physical frame, that would be true. But
I absolutely believe that the effect you're talking about would happen in these theories. I'm just saying
Right.
effects as well.
I understand.
One more question for So yeah, I want to split. So I couldn't make the connection. So can you explicit a little bit the connection with like the Fourier type of degravitation?
Yeah.
So I couldn't.
I wasn't very explicit about it at all.
Yeah.
Okay. So here's actually the connection. So
Can try to get rid of.
maybe I should write something.
No, I can.
So the simplest way to think about what Justin Curry and collaborators have talked about in a series of recent papers, what they call degravitation. The simplest way to think about it is having basically a massive graviton. So the only theory of actually massive graviton that we know of is a linearized theory. So you linearize your metric around some Minkowski background, and so this is your metric perturbations. And if you write down the corresponding equation of motion for small perturbations linearized, you get basically an equation of this form. This is just the usual, basically, term that comes from Einstein-Hilbert. So this term is something like Bob's H mu nu, for example. This comes from just Einstein-Hilbert. This is the graviton mass term. This is the mass of the graviton. And basically, you can see if you have a theory where the graviton is massive, you see you have a degravitating solution, i.e., let's say this is the cosmological constant times eta mu nu. Then clearly you can have solutions that have basically zero curvature, which is satisfied by balancing this term with this term. Yes? Where basically H mu nu is proportional to the cosmological constant divided by the graviton mass. Right? So that's basically essentially the idea of Justin Curry et al. So you introduce a graviton mass, which allows for actually degravitation. You have solutions where the metric is flat, and in spite of having a cosmological constant, it comes from this mass term. And in fact, this argument can be generalized where M is not just a number, it's an operator, which would be like the DGP case. And the point is this: in all these theories, you can always actually do the following trick. It's known as a Stuckover trick, which is as follows. You can always separate this your tensor into a part, which is also light spin 2, but then actually what looks like basically a scalar degrees of freedom. And if you make that decomposition, it turns out you can show the part of the of your massive graviton theory that's actually responsible for degravitation is actually not this part. It's actually just the scalar part. And to the extent that is true, you can actually map everything into basically what I wrote down there. It's just, in fact, actually, effectively another scalar tensor theory. At least to the extent you are focusing only on the degravitation mechanism. Basically, that's more or less.
All right, so we'll try to have Lam again at the end of the session today to hear about magnification, but let's thank him already for.